We have the privilege of having as our featured speaker Dr. Robert Papalardo. He's the project scientist for the Europa Clipper mission at JPL at the California Institute of Technology. He was also project scientist for part of the Cassini project or mission. And he has won service medals from NASA for his work. And most of his research has been centered around the icy satellites of the outer solar system. So with that, I would like you to welcome Dr. Papalardo.
Thank you so much. I'm to be here. So work all right. Happy to be able to talk with you today about the Europa Clipper mission and about Europa. Now, I'm not sure how far I can wander. It's still on the camera here. Oh, I can wander all the way to Europa. That's good. So that's the start of our show here today. I'll tell you a little bit about Europa and what makes it so special. And we'll talk about this little guy, which is our spacecraft, the Europa Clipper mission that is currently being built at JPL. I'll give you an update on its construction. We'll see how it's coming along and what its science goals are, etc.
Provide us.
And then spot.
Well, I'll tell you, I'm pinned at the moment.
Yeah, right there.
Sorry, doctor.
There you go.
All right, okay, well, this thing, well.
Oh, he's sharing his thing.
Okay, hopefully everyone can see. You can see out there online.
Dave, can you get rid of the participants?
Which?
Participants on the side.
Maybe
Yes,
Can you
I
get rid of
know.
them?
Drag
I don't think so.
Or you can shrink them. The line on the left, the far left, top of the participant.
There you go.
There.
Okay. Okay. And then we'll come in to folks for questions later on. All right. Happy to tell you about this really cool moon Europa and this really cool mission, the Europa Clipper. And in case I don't say it later, there are stickers. Take stickers later.
Yay.
Europa Clipper stickers. Okay. Now this group, I don't have to tell this group about the Galilean satellite. You can go out and see them right now with a pair of binoculars. There's the first picture of Europa, image of Europa from Galileo in 1610. And the Galileo spacecraft that was named for Galileo Galilei, the discoverer of the satellites, explored Jupiter and its moons, went into orbit in the late 90s and finished its mission in the early 2000s and made reasonably close flybys of each of the moons of Jupiter. And it flew by Europa about a dozen times. So the Voyager spacecraft also went by Europa, but the resolution wasn't nearly as good. The flyby distance was much greater. So most of what we know, what I'll talk about with regard to Europa, is from the Galileo mission, and some is from Earth-based telescopes as well. Okay, there's Europa, image mosaic from Galileo, relatively true color. Okay, probably a little bit paler than that. Great. And you can see it's very unfamiliar. It's not like Earth's moon in appearance. There are a few craters, but really very few. That's one over here. That's one over here. Oh, I should point with the arrow for the folks online. Right. That's a big impact crater, and that's a big impact crater, and you can see some rays and light, but there aren't a lot of them. And from the number of impact craters, the relative drift of impact craters, large impact craters, we can estimate the age of Europa's surface as about 60 million years. Sounds like a long time for us, but in terms of a planetary surface, it's about 1% of the age of the solar system. So something has repaved Europa since the time that dinosaurs roamed the Earth. It's mostly an icy surface. We'll talk about that in a little bit. Most of what we see is ice and contaminants in the ice. It's a weird place and probably has a global subsurface ocean under that ice. Closer up, the bright whitish areas are crisscrossed by ridges and grooves. We'll look at those in a bit more. And the dark areas are generally this chaotic terrain that looks like, I don't know, like the older terrain was cooked from below in some way and broke apart, aptly named chaos terrain. This is what we think we know about the interior of Europa. And we know that mostly from, well, in part from gravity measurements and in part from magnetic measurements. So gravity measurements tell us how centrally concentrated the stuff of Europa is. So we can tell from the gravity measurements that there's probably a dense core surrounded by less dense stuff and surrounded by less dense stuff still. And those layers are probably iron or iron-rich layer, a rock-rich layer, the mantle, and then an H2O shell about 100 kilometers thick. The gravity data doesn't tell us whether it's liquid water or solid ice, and it's the magnetometer data that tells us that it's probably liquid water down there. We'll get to some of the indications of the thickness, but in general, the thought is that that icy shell is probably something like 20 kilometers thick, something like 16 miles thick. Earth, Europa probably has, if it has 80 kilometers of water, I didn't say it's about the size of Earth's moon, but it has probably 2 to 3 times the volume of water of all of Earth's oceans combined. Plus, it's a thick layer. Earth's oceans are several kilometers thick, 7 or so is about as deep as this ocean scale. Okay, the magnetometry. So I mentioned gravity. We can tell how centrally concentrated it is, but also from the magnetic field around Europa, and Europa's magnetic personality, we can, that's actually the best evidence for an ocean within Europa today. So Jupiter, like Earth, acts as a big magnet. It has a north and south pole. It has the biggest magnetosphere, a region of magnetic influence of any planet of our solar system, the biggest planet, you might expect that. And if you could see the magnetosphere of Jupiter in the sky, it would be greater than the diameter of the full moon that's viewed from Earth. So Europa is traveling in its orbit around Jupiter through that magnetic environment. But Jupiter is spinning really rapidly. And so the magnetosphere of Jupiter is traveling faster than Europa orbits. Jupiter rotates in 10 hours. Europa orbits in 85 hours. A couple of things that means. We'll get to the fact that particles, charged particles trapped in Jupiter's magnetosphere are slamming into Europa and the other moons of Jupiter, Io's there, and into our spacecraft that's going to be making flybys. It's a dangerous environment in terms of the really high speed particles, energetic particles that are slamming into these moons. We'll see that actually that plays an important role in the potential habitability of Europa's ocean. We'll get there. But the story here is that when the Galileo spacecraft flew by Europa, it noticed a little mini magnetosphere, or at least a blips in the magnetometer signal as the Galileo spacecraft flew by Europa. And so the first thought was, oh, maybe it has a little mini magnetosphere. But then when the Galileo spacecraft flew by in a different orientation of the Jovian magnetosphere relative to Europa, the magnetometer signal was reversed. So something weird is going on, that Europa's this magnetic signature at Europa changed over time. And so what we're pretty sure is going on is that Europa is creating its own little mini magnetosphere, in a sense, mini magnet, because it's moving through the magnetosphere of Jupiter, where Jupiter's magnetosphere is moving past it, because it's moving past it. So the best analogy for this is if you have your keys in your pocket and you walk through the metal detector at an airport or something, right? It beeps because you've taken something conductive and moved it through a big magnet. And the same kind of thing is going on. Something conductive inside Europa is setting off the metal detector, if you like, of the Galileo spacecraft. And that something conductive, we think, is a saltwater ocean. The core of Europa is too far away, even though it's probably made of metal. But the fact that saltwater oceans should be able to conduct electricity is probably what's creating this magnetic effect. So as a geologist, I and others, other geologists, were trying to find geologic evidence for an ocean in Europa. The really best evidence comes from the magnetic measurements. So what's maintaining an ocean inside of Europa? A moon the size of Earth's moon in the frigid outer solar system, where Jupiter is 5 times, right? The distance from Earth to the Sun is the distance from the Sun to Jupiter. You'd expect ice there, but you'd expect probably these moons to be frozen solid. Well, what's going on is Europa orbits in its eccentric, slightly non-round orbit around Jupiter. We're pointing to the upper left there. And this is exaggerated, but Europa gets a little closer and a little farther from Jupiter in its orbit. I thought just for fun, I'm going to try this. I'm trying it before. Now I have my giant inflatable Europa. We try a little bit, a little mini demo in a moment. But Europa flexes as it gets closer and farther to Jupiter in its somewhat eccentric orbit. And this flexing, exaggerated here, not for scale, creates heat. Kind of like rubbing your hands together or Play-Doh back and forth, generates heat. And that's enough heat to maintain an ocean within Europa. I'm going to stop this movie for a minute so we won't get all really dizzy. So let me get a volunteer. This is easy. So first we need a volunteer, just be Jupiter. Jupiter is just going to stand there. If you want to, you can rotate it. Sure. Why don't you come up? Because I noticed your Jupiter like it's really just like standing in the middle of Jupiter. You can go around and around, but I think you get really dizzy. So imagine that you're still. Okay, and then if I can get someone to help out with Europa, sure. Here, thank you for the camera. See if we can make this work.
Sorry.
Okay. You're gonna help with Europa, and there are a couple of tricks here which will help, I think, us orient. I think we'll maybe be the sun. Or maybe a flash bulb would help too. Mark, maybe you can help with maybe the sun and just, kind of stand over there and be shining at Jupiter and Europa. And, go behind the projector, and that way you're in line. You will, yes, you'll be orbiting Jupiter, of course. So trick here is to make sure that most moons of the solar system, well, this group again probably knows, like Earth's moon, are tidally locked, so they always show the same face toward their parent planet, just like our moon does. So I'm going to try to find the spot that's always facing Jupiter, because I have to think about this, right? And it's about here, and it's opposite. Make sure I find it right. Okay. That side of Europa is always facing Jupiter, so that's the subjovian point. Somewhere over here. And so opposite of that will be the anti-Jovian point somewhere over there. It's about right. Jovian. Okay. Oh, but I didn't, yeah, you're facing Jupiter. That's right. Okay, that's good. And if the same face is always facing Jupiter, then there's a part of Europa that's always leading. That's over here where you can't see, it. And there's a part of Europa that's always trailing in its direction of motion. So you're going to Europa, walk around Jupiter, and the challenge is to keep the subjovian point here facing toward it. Oh, other way. Other way. Thank you. Yeah. There you go. There you go. Perfect. Perfect. Now, yeah, you can rotate. You're going around once every 10 hours. I'm going once every 85 hours. Okay, you can, again, you can imagine this spinning. Okay, now there's another trick, because as you go around, the orbit is a little bit eccentric. It's only 1%. The eccentricity is 0.01. But we can exaggerate it so that you can get a little closer to Jupiter as you go around, and then when you're over there, a little farther from Jupiter. Yeah, we'll exaggerate. That's good. So hold on a second. When Europa's a little farther, it's going to relax. It's feeling less gravity from Jupiter, and these parts kind of come in a little bit, and then come around where you're closest to Jupiter. A little further. And then when Europa's closer to Jupiter, it's stretched out. And so that's what that movie was trying to show in terms of getting closer farther. But also I wanted to point out that this idea that the points on Europa are kind of fixed, relative to Jupiter.
So Europa does not rotate on an axis?
It does. Okay, good point. Thank you. The sun is there. It does, just like the first one does, because watch what happens when once. Let's broaden the sun a little bit. So the whole thing is. Oh yeah, that's good. Okay, so right now this area of Europa is lit, and now go halfway around, and that area of Europa is now dark. Right, its month is its day. Just like Earth's moon, its month is its day if you're on. And that will be key later if we have time to do the second part of the demo. Thank you. Appreciate it. You're welcome. And Jupiter. It's a junior highway. Good old friend. All right. There you go. So there's a lot going on. And we haven't even brought our spacecraft into the picture yet, which I'll try to do later, but we go without crashing into Europa and Jupiter. And ridges. That ridged part of Europa is cross-cut by these things. The ridges generally can travel in pairs. So with a trough in between. Galileo image about something like 20 meters per pixel, I think, that we're zooming into here. Colorized by lower resolution data. Most common feature on Europa are these ridges. We don't know how they form. Their ideas. We think maybe warm ice has come up and pushed the surface up and caused a crack. Sort of like a tree root growing under a sidewalk or something. But there are other ideas. Maybe something's come out of these cracks to build the ridges. Maybe there's compression involved. Maybe there's extension involved.
It looks very scratchy.
Yeah. But it's probably not that something has come and flowed because it's really cold on the surface there, but that things have pulled apart or maybe pushed upward and caused these cracks. And then, and there are places where instead of a ridge, we see something that's called a band. Oh, I didn't say how big the ridge was. It was, there maybe 2 to 5 kilometers across. So I can serve as a little bit of a scale bar. This thing's more like 20 kilometers across. If you go to Photoshop and kind of cut this out and push the edges back together, what do we see? You see something that looks like one of these double ridges or a curved version of it. So these ridges are places where sometimes the whole icy shell just holds open somehow because of the tectonic forces, and new stuff has come and filled that gap in between. But we think it might be like the mid-ocean ridges on Earth's seafloor. Nothing to do with the ocean. Well, I should say nothing to do. So instead of rock, it's ice that's coming up and oozing into these cracks. So we saw craters, we mentioned craters a little bit. One of the ones we saw before that had rays around it is this one, Quill or Cook, or if anyone's Welsh, you can correct me in the pronunciation of W-Y-L-L. It's about 20 kilometers across, and it's very flat. Again, it's not like the lunar crater in terms of our movie, where there'd be big bowl here. Very flat, because when this thing formed, that ice shell is relatively warm, or still is relatively warm underneath, and like poking a warm cake, it relaxed straight back up and filled that crater. Oh yeah, there's the name. This is a bigger impact structure, Tyre. It's about 40 kilometers from here to here. And we think this is a place where the impact of crater was so big that it penetrated probably all the way through the ice shell to liquid water. And the cold surface ice collapsed into that hole and pulled the surface to form these concentric cracks that kind of look like a bullseye. There are only 2 of these on Europa. One of them was, the other one was something we looked at on the global view. Dark spots. So this one's about 25 kilometers across. We've seen a lot of dark reddish stuff. Again, the color is a little exaggerated here, not terribly. It would look sort of ruddy ochre if you see it, if you saw it with your eyes. So that's all this dark stuff. And there are ideas. I need to update this diagram. I knew there's something I needed to update. We can look at, with the Galileo infrared instrument, we could look at brightness, reflectance, as a function of wavelength in the near infrared. These are microns. And the ice shows very particular dips and wiggles. And the dark stuff shows slightly different, more asymmetric, shallower dips and wiggles. And there are people who do it for a living who will fit these dips and wiggles on Europa, other planetary surfaces, to try to understand what the materials are. One idea, let's see if I can do the animation here. One idea is Epsom salt, magnesium sulfate. The other is sulfuric acid hydrate, which is battery acid. One would be great to take a bath in, the other not so much. What might be going on is that it's magnesium sulfate that comes up to the surface from below, but then those charged particles in Jupiter's magnetosphere alter it, change it into battery acid on the surface. But a recent paper, what I need to change is, or add here, is a recent paper, recent 5 years ago or so, says that sodium chloride, table salt, if you're radiated, will turn kind of brownish ochre in color. So it could be that the color, because Epsom salt isn't actually red. So this is the infrared. What's happening in the visible part of the spectrum? It could be that there's table salt in there, any sodium chloride that came from Europa's ocean, and that's what's giving it the red color. So we need to understand more, because it can tell us about the chemistry of the ocean and habitable, that ocean might be.
The coloring is very similar to Poland's, like found on Pluto.
Right,
I can talk.
Randy's, I can repeat.
Okay. The coloring is very similar to Poland's, like found on Pluto or Charon. But is the chemistry similar in that respect?
I don't think these kinds of absorptions on infrared are seen in those bolins, and you're right, the color through the visible is similar, but is there a consistent story that can explain that visible and infrared? And there. So I'd have to think about the slope, you know, there are folks who do this for a living and think about the slope of how red is red through the visible. And I think it's not quite as red as those outer solar system dark organic things, but organics are what we really want to know if they're organics. They're mixed in here as well.
So, and the Poland's, the other Pluto Charon are more ammonia methane.
Right.
Than,
That's right. And you're not, and it's harder to get ammonia and methane, probably not possible at Europa, because it was too warm there when Europa formed, as compared to the distant outer solar system that has the more gunky, the more volatile ices and those gunky folds. And also at Europa, high energy particles would rip apart those organics pretty quickly. So we're going to search for organics, but if they're there, they're probably pretty young, not yet ripped apart by the radiation. Okay, let's move for the other type of terrain, chaos terrain. I like this one because I get to show lava lamp. What's this crowd probably remembers lava lamps. So we see these things on Europa. They're kind of 5 kilometers across. They're called lenticulae, Latin for freckles. And what we think they are is places where the ice shell is acting like a lava lamp, where warm ice, oops, I have to point over here, where warm ice has risen up and pushes up the surface, or maybe makes it out onto the surface. And that's because the bottom of the ice shell will be warmer. That's where it's melting in contact with liquid water. The top colder, not just colder, 100 degrees Kelvin. I'm not going to convert it. Ask Google, it's minus 300 something Fahrenheit at the surface, but it's just, you know, 0 or maybe minus 10 degrees Celsius at the ice ocean interface there. So kind of like a lava lamp, the warm ice will be buoyant and move up toward the surface and form these features, we think. And that's kind of a big arm wavy thing, but it's hard to make these. So here's one of the big chaos areas, Connemara chaos, right near the trailing points of Europa. There it is. Trailing. And using the Galileo images, we can zoom into different scales of image and look at Connemara chaos up close. So from far away, we can see that it's made of these little blocks. Kind of looks like sea ice that's broken apart, but it's not. It's frozen today. You can see something that looks like, well, one of these big grooves cutting through it now, like it's completely solid ice. And we're zooming in on this big cracked block, which is about 5 kilometers across. The East Coast, I can say about the size of Providence, Rhode Island. That's probably not very familiar here. And as we zoom in, it really starts to look like a place. It starts to look like Monument Valley or something, where you see that there are these big cliffs and then shallower bases, right? So these blocks have moved apart and cracked and broken. You can see some tiny craters. Those are secondary craters tossed out, we think, from Quill almost 1,000 kilometers away. And here we are going out into that part that's between the blocks. There's a sad looking ridge on one of the blocks, and now moving back out. The Titanic would be like this big. Lions.
It almost looks like fossils too.
Right. But these things are giant 500 and kilometer scale. it doesn't look like a smooth skating pond, like there was just liquid water that came out and froze, but if water is exposed at Europa, it's gonna froth and bubble and churn, and maybe it could look like that. But I think more likely it's related to maybe some of this warm ice that's come up from below and moved the blocks on the surface, kind of like crowd surfing. Randy's probably very familiar with that. He's had an accident. That move these blocks around. You have a question with that?
My question is, there were a lot more radiation and charged particles in the trailing there.
That's exactly right. Are there more particles hitting the trailing edge of Europa? Yes, that's exactly right. So we had Europa going around Jupiter, and that's my meeting point, the meeting trailing, the meeting. Right, walking around Jupiter here. And so the charged particles are going faster than Europa is orbiting. So they're slamming into the back. Exactly right. And the back is redder, darker than the front. So that's consistent with the charged particles having something to do with the coloration of Europa's surface. Yeah. So if you want to put a lander on Europa, you might think of maybe the leading side would be a safer place for it. Relatively recently, how many years ago is it now? Losing track of the date. It was relatively recently before the pandemic, so maybe 6 years ago or 7 years ago. Oh yeah, it helped the mission get going. It was probably around 2013 or 14. Hubble Space Telescope observations in the ultraviolet showed a glow on the limb of Europa. And that glow was seen consistently from orbit to orbit with Hubble. And if some of you know the Cassini mission and Enceladus, there are plumes at Enceladus. And the thought is maybe there are plumes at Europa. And if there are plumes of vapor at Europa, the charged particles will strike them, make them glow, kind of like the aurora of the Earth, and we see them. But then they were gone again. These things, if they exist, if these are plumes, they're transient. Or they're also right near the detection limit. Maybe they're not really there. And this is something we need to understand and find out from further investigation from spacecraft. So, big question is what really drives Europa exploration for NASA and interest to the public, and the big picture question is whether Europa has the so-called ingredients for life, whether that ocean could be a habitable environment. And we're not talking, people living down there, but we're talking micro single-cell organisms. Could there be life down there? So the ingredients for life are water, essential elements, chemical energy, and time, stability. So water, Europa probably has more water than all of Earth's oceans, and it might have water within the ice shell as related to those chaos areas. Maybe there's melting associated with them, we're not sure. Essential elements, what we mean there are the elements that build organic molecules, things like carbon, hydrogen, oxygen, phosphorus, sulfur, nitrogen, chunks. And those are probably there. They're in most planetary bodies from the formation of the body and then from later impacts. But we want to know and not guess. We want to understand, is there nitrogen in Europa's ice shell, for example? Chemical energy, that's really the hardest one and probably the most important. What we mean there is, are there the chemical species that can get together and power metabolism for life at Europa? Under Europa's ice shell, it's not going to be the sun that powers life, photosynthesis, because sunlight dies out after a meter of ice. We're talking kilometers of ice. It's pitch black down there. But there are many places on Earth where it's chemical reactions that power simple life, chemosynthesis instead of photosynthesis. And so we need to understand whether there are the reductants and the oxidants, if you remember your high school chemistry, that can get together and power life, kind of like the poles of a battery. That's a hard thing to figure out from the spacecraft, but it's something we want to try to do with Europa Clipper. Oh yeah, show a cool little movie. We know that on the Earth's ocean floors, there are materials pouring out based on interaction of water and hot rock. The water leaches out chemicals, and they spew out in these things we call black smokers, and they power an ecosystem in their neighborhood, like these giant crabs and the like, because they're feeding off those microbes that are in turn feeding off the reaction of the reductants that are pouring out of these black smokers and the oxidants that are coming from above, from the surface of the ocean where air mixes in. So might we have something like that going on way down in Europa? So if there are reductants that might come out of these reactions of hot rock and water, what about the oxidants? Well, that the charged particles slamming into Europa, largely on the trailing side, but really distributed all around, they break apart H2O. They break apart the ice into hydrogen and oxygen. Now there's other stuff too, like I said, sulfur and maybe magnesium sulfate, and that gets ripped apart too. And so you have these little fragments, and those fragments, there's lots of oxygen hanging around, lots of oxidants on the surface of Europa. The hydrogen floats away, the oxygen stays behind. If that stuff can get into Europa's ocean could be as oxidizing as Earth's oceans are. There are lots of oxidants on the surface. Can they get in? So we want to understand the geology of Europa's ice shell and the transport mechanisms. How does Europa get stuff from the surface to the interior? Does it do it? How does it do it? And we want to understand how Europa gets material from the bottom to the surface, because then if there's life in there, maybe we can detect it. And we talked about this idea of the lava lamp, convection, ways in which warm ice might rise from the bottom to the surface. And also if there's melting near the surface, melt water is denser than ice, and so it'll sink down into the ocean. So that those are ways that Europa's ice shell might circulate. And you'll see our little spacecraft is going to investigate that. Stability is essentially how long has this gone on? How long does it take for life to develop? We don't really know, but if Europa's ocean were just 100 million years old, we might say, well, maybe that's not enough time for life to develop. If Europa's ocean's 4 billion years old, then there's plenty of time for life to develop. So that's a factor as well. Yes.
Can we tell if the thickness of that ice, of that ice layer, is it consistently thick, or could there be thin spots?
Right. This diagram shows thin spots. Do you want to say it again into the mic?
The consistency of the thick ice layer, could there be thin, like little thin spots?
So whether there could be thin spots depends on how thick that ice shell is. If it's really thin, a few kilometers, then there can be thin spots. If it's really thick, then the ice should be warm enough at its base that it flows faster than it can thin.
Maybe for those, I'm finding those little blisters are
Right.
thinner.
So could it be thinner where those little blisters are?
So
Probably that would mean it's pretty warm down here and the ice actually flows pretty quickly. Like glacial ice is quick in our time scales here. So Yeah, I was just reading a paper about this that argues that, it's tens of meters is the most topography we're gonna get at the base of that ice shelf if the ice is warm. But if it's cold, then it can support differences. So probably it's relatively uniform, but relatively, sorry. Where it can vary is kind of globally. So it could be, thicker at the poles where it's colder in general, thinner at the equator, but not so much local on the local scale. That's the latest thinking anyway.
You know how it expands a little bit when
Yes.
it's going around? Could that over time make it thinner?
What we think that does is it can crack the ice. And I'm trying to think if I have a good diagram here in this, hold on a second, this one will do it. So that surface ice, sorry, I'll point with the arrows for online, that there's a cold layer here, cold brittle layer, and a warm flowy layer, ductile layer. And so that upper layer is where we think the cracking occurs, and then that lower warmer layer is where the ice flows, and really it's, one grades into the other. So the stretching and contracting, I meant to say, it's 30 meters that Europa will flex as it orbits around Jupiter. That could crack that outer cold layer, maybe down to the place where there's the warm ice and fans. And when these things rise up, might there be local melting because there's saltier pockets, and salt will lower the melting temperature. And so, again, these are just ideas that we want to test with our.
I bet you can't wait for that goes out there.
It's been a while, yes. So let's go on to the goals of the Europa Clipper mission. Am I okay on time? I think. We're good. So Europa Clipper has 4 main objectives and one kind of cross-cutting objective. We want to understand the ocean and the ice shelf, right? What's the interior of Europa like? We want to understand the composition. What's that dark stuff? What does that tell us about the composition of the ocean and potential habitability? We want to understand the bizarre geology on the surface. And what does that say about where is there liquid water and the history of Europa and how Europa kind of works? But there are a couple, oh, sorry, I said 4, there are 3, that was 3. Then the cross-cutting theme is kind of number 4, is Europa active? How active? Are there plumes? Is Europa cold and dead today? And we're wrong to think that it's active today. Maybe it was active 100 million years ago, and it'll be active again 100 million years from now, which is one possible model. And something else our spacecraft does is we'll be able to image the surface close up and use other techniques as reconnaissance toward a future lander. Because we would love to go to the surface and we really want to search for life. Right? We're looking for habitability with the Europa Clipper mission. You want to search for life. You want to land on Europa and you want to dig and sample that dark stuff. You want to get below the depth where radiation processes the surface and destroys organics. And that's maybe tens of half a meter or so below the surface. All right, so how are we going to do this stuff? There's our spacecraft. We have a little version. Come see afterwards. And this is fun because we didn't have the model last time I gave one of these talks. So, there we go. Let's see if I have it labeled. Oh, good, I do. There we go. Okay. So, I'm gonna try to orient it the same way. There we go. There we go. So, I like to think of Europa Clipper as, I don't know, some kind of bug that I can't quite figure out. Dragonfly. Yeah, it's kind of like dragonfly, but this is dragonfly mission, so I don't think it is that one. Right, it has a magnetometer boom, it's kind of its tail. You're seeing the flyby configuration. Change a little bit. It has a high gain antenna. During the flyby, it's pointing up. I like to think of that as the head. So we're not using it during the flyby, it's pointing the wrong way. It has these wings, the solar rays, 5 panels on each side. From tip to tip, it's bigger in size than a standard US basketball court. Let's see. There are a bunch of instruments that are, let's start with the downward pointing. Those are the ones that are looking down at Europa when we make the flyby. Those are the cameras, spectrometers, thermal instrument. And then there are a couple of mass spectrometers, things that sniff, well, again, we'll look at a minute, sniff and sense the dust and very thin atmosphere. So those are pointing in the direction the spacecraft is moving. So that's what the spacecraft is for this. So the remote sensing instruments are that way, and going that way, flying that way, are the spectrometers to sniff the atmosphere and the dust. There are radar antennas, two big ones, 16 meters long, and 4 smaller ones. And so we have 2 wavelengths of radar to penetrate through the ice shell and tell us if there's liquid water down there. Because long wavelength light, essentially radiation, right? Radio waves beamed through cold, clean ice would bounce off liquid water and back to the spacecraft, because cold, clean ice is transparent to very long wavelength waves. And that's how we're going to try to tell what's going on in the subsurface and what's causing exchange of material at the surface and the ocean. Okay, so I'm just going to run through the Europa Clipper science investigations here with this little illustration. So one is gravity. We mentioned gravity for the Galileo spacecraft. The Europa Clipper spacecraft is planned to make 49 flybys of Europa, and the Galileo spacecraft made a dozen. And the Europa Clipper mission is equipped with instruments designed to investigate Europa's habitability. The Galileo mission was not specifically designed for such. So we'll understand how Europa tugs on the spacecraft when we make flybys of it, of Europa, to understand how that ice shell is flexing. Yes, question.
That boom is, are you worried that any of the particle stuff might hit the boom?
Not particularly, because it is coated with materials and that will protect it. But there are also particle detectors that we want those particles to hit and are designed for them to hit, so we can detect them and understand their composition and their energies. Actually,
Pretty exciting, huh?
oh, it's all wait, there's more. So there's the gravity. Magnetometry and plasma, 2 different instruments. Magnetometer, this boom has 3 magnetometers on it, and we have plasma instruments as well that aren't going to show up at this scale, but trust me, there's a plasma instrument on the bottom and the top to understand the magnetic environment. So instead of dozen flybys or 49, to understand not just if Europa has an ocean, but how thick and how saline, how conductive that ocean is. And plasma instruments to get at those charged particles, because we kind of need to subtract that out to understand the magnetic field of Europa. Imaging, of course, to
Yeah, there's a question there if you want to answer
oh,
that.
sure. The particles hitting the trailing side of Europa because the magnetic field is weaker. No, it's because the particles are moving with, they're trapped in Jupiter's magnetosphere. They're going around Jupiter at the same rate Jupiter is rotating every 10 hours, whipping around Jupiter. Europa's orbiting Jupiter every 85 hours. So these particles slam into the back of Europa with very high energies, kilo and mega electron volt. Imaging. So we'll understand Europa globally. Let's see, the Galileo mission has about 10 to 15% of Europa imaged well enough to distinguish, like those ridge trains and chaos trains. Europa Clipper will do 90% or so, and at about 100 meters per pixel, and it will see spots at up to 1 meter, even half meter per pixel, you'd be able to see maybe that carp if it were that's holding the projector, if it were on Europa, certainly the steel if it were on Europa, and the monolith. Infrared. So we'll look for the chemical signatures of those salts and search for organic materials. Thermal, we'll look for places that are glowing warm enough to emit light or emit heat, I should say, and work to detect those, just like the Cassini spacecraft was able to find hot spots at Enceladus. And when I say hot, I mean instead of the surrounding 100-degree Kelvin temperatures, maybe they'll be 170 degrees Kelvin. Right? It's still pretty dark cold, but hot.
There's another chat.
Sure. Monitoring there. Oh, is that
Not helpful.
maybe we're not doing no on sound here. No. Radar. So I mentioned the radar antennas, 2 different wavelengths, being able to send a signal actively, have it reflect back to the spacecraft to try to search for liquid water and the structure of the subsurface. And you can see a picture of Europa is slowly building up from these. Ultraviolet will be used to look for glowing gases that are hints of plumes, or really to just understand Europa's very tenuous atmosphere, about as thick as Union's atmosphere, which varies and will glow depending on the orientation of the magnetosphere with respect to Europa.
With the detection of organics, is there any capability of the
Wait a minute.
the probability, left hand to right hand?
Sure. Let me repeat that. Go ahead. You got it.
Sorry. With the detection of organics, is there any ability or capability of the spacecraft to distinguish between the correlities of left hand and right hand correlity?
We can't distinguish chirality whether a molecule is left-handed or right-handed with Europa. That takes pretty sophisticated techniques. A lander, that's been discussed as a goal of a lander. I'm not sure whether the Dragonfly mission can do that. I think that would be interesting to find out. What else do we have? We have 2 mass spectrometers. Those are the ones that are forward pointing when Europa is flying past the satellite. One is to understand the atmosphere, the gases. It sucks in gases, it ionizes them, it bounces them back and forth. You know, in case any of you know mass spectrometers and how they work, bounces them back and forth as many as 40 times to this meter-long tube to separate them in their time of flight, and that separates out their masses. And this will have just exquisite mass resolution to tell us the detailed composition of those gases. And then we can detect dust with a different instrument that's knocked off the surface by micrometeorites, or if there are plumes, come out in plumes and measure the composition of those dust particles. That's it. That's it. That's a lot of instruments. That's pretty good. So that's our suite of, depends on how you count, 10 investigations. There are 2 cameras. Okay, now we get to see some cool pictures on the status of where things are. And again, give me an idea of time because I get excited.
Oh, you
go on. So this is a somewhat exploded view of our spacecraft, not quite in the stowed configuration, but it's stowed. Those solar panels are contracted in a little bit, but it gives you an idea that there's the high gain antenna. RF is the radio frequency module, i.e. the telecommunication system. Avionics module, that's where the electronics are. They're in what we call a vault. The Juno spacecraft is similar. Thick aluminum, something like an inch. Thick aluminum because it stops those charged particles and protects the electronics down in there, so they'll survive longer. The nadir platform, this diagram points to the top of the nadir platform, which is very complete. So this is the part that looks down at Europa where the remote sensing instruments are. radiator, excess heat is expelled. And that's the scale of the person next to our spacecraft. There are no astronauts on board. Astronauts, and there it is on its side. Apparently it would reach from the foot to the crown of the statue of liberty. We can, when testing this thing, assuming we get the solar rays at JPL, they might be mounted at Kennedy. We can only unfurl one side at a time for testing because it's so big. And building, everything built in. And here it is, it's coming to fruition. I've been working on the Europa mission concept since 1998. If you're really interested in the history, from 1998 to when the mission got going in 2015, there's a book called The Mission by David W. Brown, and it'll tell the story, and that's like the start of our mission, 2015, and a whole book leading up to that point. And here it is being built. This isn't it, that's a test model of what it's going to look like and used for dynamic testing, but this is it. And they're next to each other in the high bay at JPL, which is somewhat confusing, but it's nice to get an idea of, oh, it's kind of going to look like that. And the avionics module is stacked on top of the, oh, I forgot to point out the propulsion module to which the telecommunications bit is attached. What else can I tell you? It's on this thing they like to call the elephant stand. To hold it up for now, anything red will be pulled off before launch, like they used to say before flight. Let's see. This shows 2 example solar array panels. That's used for like shaking tests and is it going to survive launch and that kind of thing. That's what the dynamic test model is used for.
Speaking of the power, will it be radioactive decay powered, or is it going to be old fashioned?
Solar arrays. Yeah, we're using solar just like Juno, and that's why the basketball court size extent of the thing. All right, let's look at a little more. This is the avionics module. Put it on. I'm so sorry, I missed this happen. They put it on this giant rotating turntable because sometimes you want to work on one side or sometimes you work on the other side when putting the instruments on. So there's the nadir deck. Sorry, I'll point to those online. The nadir deck, there's the wide angle cameras, that black thing. These are the star trackers, the way it knows its orientation in space is to see where the stars that are out there. Come to JPL, see this thing being built, or like you see the 24-hour cam.
There's another,
Yes.
There was another chat question that came up, that is, does this mission run fly by any other than?
Yes, the first flyby is of Ganymede. I'm not gonna remember the number. It's something like 7 or 6 of each of Ganymede and Callisto. We'll see it in a little bit. The science of this mission is only at Europa. We might do some calibration at Ganymede, a test run, essentially, to know that we've got the procedures down. But the science will be concentrated at Europa. Okay, it's one over.
It's a very quick question. How many Star Trackers? I'm just curious.
There are 2 star trackers. So you can see both in the picture right there.
What are you gonna launch it with?
Falcon Heavy is going to launch this thing. We'll talk about that in just a minute. Here's the high gain antenna. No, another question. Sorry. Go ahead.
Question I just like, can't use dragonfly, I was in a bat.
Kind of like a bat. Let's work with that. These bangs. The high gain antenna is 3 meters across. They wouldn't let it into the clean room until it was cleaned. It was up here in Sunnyvale, California for a while. No, we can't accept that thing. It's filthy. But they cleaned it up, brought it to the airlock, cleaned it some more, and now it's in the high bay. And it's black because it's some sort of carbon fiber that won't have electrostatic discharge.
I just love that California is so relevant in space stuff.
California is extremely relevant. The solar panels are being built at Airbus in the Netherlands. It's contracted through Flight Physics Lab in Maryland. It's a long story. And yeah, I love this. They're, they each get their names PXP2 panel being built there at Airbus, and with all the cabling being distributed across it. The detail, yeah, a lot of detail. The radar cares about every one of these cables and where they are and whether they're going to cause electromagnetic interferences. They have to model them all. Ethemis is our thermal instrument. It's hard to recognize them with their little blankets on. So they're checking the multi-layer insulation MLI that goes on the outside and blankets it. I think this is I think the red thing there is probably the detector area of the telescope of the thermal imager there. This is the upper. There are two units, if you like, of the plasma instrument pins. Plasma instrument for magnetic sounding. And that red cap is on one of the sensors, and there's another sensor up top. So we can see the whole sky, essentially, two up here and two down below on the spacecraft. That was temporarily on for its patterning of the material. The infrared instrument in testing, you can see the very proud team here that assembled the infrared spectrometer for testing.
You're all wearing masks.
Yes, oh yeah. And so part of that was COVID, but part of it is to be cleaned in the clean room with your instrument.
Yes.
The dust analyzer team at the University of Colorado, having built the surface dust analyzer, SUDA. It's really moving to see these instruments come together and starting to be delivered to JPL. About half of them are delivered to JPL now and being integrated on the spacecraft. For Star Trek fans, in my office, I have this a picture of the gas mass spectrometer, mass specs next to the Genesis device. They're in scale and look, and that's the meter-long tube that the ions bounce back and forth in to get separated and detected. This thing is just astounding. This is one of my two deputies, Kaya Korth, out in the woods, deep woods of Germany, not for socializing, but to calibrate the magnetometers. Why? Because that building is made of wood without a single nail, single piece of metal that will disturb the magnetometer calibration. They can tell when a truck or car goes by far away because they can sense it magnetically. This is a view of the clean room at JPL, 24/7 live stream going on from the high bay. Took me a while to figure out what to do. And we're going to have a press release on this soon. They're installing the reaction wheels underneath the spacecraft that maintain the orientation of the spacecraft. Just love that.
That would be a great caption.
Yes, they did. So look for a press release on the reaction wheels that are coming very soon. Meanwhile, these guys on the right, or people on the right, as else, are looking into the top of the ball. The open part is the z-axis, which can be on top of the spacecraft and stacked up here on top of the propulsion module. So they're installing some electronics, and again that the nadir deck is I think over here in this view. Again, you can see that wide angle camera, little black thing. Oh, let's see if it works. Let's try this. There it goes. There it goes. Live feed of, bring you to the YouTube play, and there's the live view right now. They're not working now, but they work the day shift now. They'll go to 2 shifts. I think it's in January. And if we have to, we'll go to, oh, it's not on this screen. Oh, I guess I'm just sharing. Sorry, I'm just sharing PowerPoint. So you're not seeing what I'm seeing. Unless I stop and go back. Share screen. Whoops. For all participants. Yeah. Wait. Sorry, I'm messing this up. There it is. So there's the live view from JPL. I don't know why the clock's always 3 minutes fast. They're trying to figure it out. So there's how they left things today, and we'll come back to it tomorrow morning. So it's to take a moment to share it back to the PowerPoint presentation. Okay, so go to bit.ly/clippercam, and that'll take you to the YouTube link of the live feed. Okay, how are we getting that? Oh, I did put my Falcon Heavy picture on. There you go. SpaceX Falcon Heavy, really clever idea. We couldn't figure out what's the right vehicle. Artemis is launching today, right? Tonight. We thought we'd go on the big rocket, on the Artemis rocket, but it wasn't ready. Right? It wasn't ready. NASA had a competition essentially to say, okay, who out there can launch this thing? And with the amount of throw from the Falcon Heavy, we can use a Mars gravity assist to get us out to Jupiter. So Earth launch, it'll fly by Mars about 5 months later, back around past Earth again, and then out to Jupiter, and that'll take 5.5 years to get us there. The launch period opens October 10th of 2024, so a little less than 2 years from now, and it's open until the end of October that year. This is what we do when we're at Jupiter. Looks like spirograph. And if you know a lot of land, you know spirograph. And our tour design is really clever. I'll come back to that in just a second. But down here on the lower left are some of the things we do. Launch date, or the launch period opens. As I said, arrival date will be April of 2030 at Jupiter. It's another year before we make our first Europa flyby. The tour at Europa lasts a little over 4 years. In resonance with Europa. So that means every time Europa goes around, either 4 or 6 times, Europa Clipper encounters it again. So about every 2 or 3 weeks, Europa Clipper would encounter Europa. Here we are with 49 science flybys, 53 total of Europa, 7 Ganymede, 9 Callisto, 79 total Jupiter orbits. And we not only dispose end the mission by crashing into Ganymede. Question.
What is the lifespan of the instruments that are going to be on this satellite?
Right. Everything is designed for a total ionizing dose of radiation of 3 megarads. So and they have to be qualified for 14 years. So they're actually doing things like running the cryocooler on a couple of these instruments for years to build up the lifetime and prove they can work for a long, long time. But the limiting factor is really eventually the radiation. But you know, there's a factor or 2 in there, and it'll probably live twice as long, at least.
Why is there no worry about contaminating Ganymede with why are they not worried about contaminating Ganymede with the disposal on the surface?
Yeah, so we don't want to crash into Europa. If we do, we probably won't contaminate the ocean because there needs to be less than 1 in 10,000 chance of contaminating the ocean. We've done the math essentially to show that to be the case. You can't contaminate it with a single organism that's hitchhiking. So that's a combination of spacecraft being clean and the mechanisms to transport Europa being slow and arduous. Ganymede has an even thicker ice shell, probably 100 or 150 kilometers thick. Its surface is probably 2 billion years old on average. Well, the younger areas are probably something like 2 billion years old. So planetary protection is not too worried about crashing into Ganymede for those reasons. Let's see. So we end up with something kind of like this, a web of flybys, Star Trek fans again, like kind of like Folian web, right? But maybe the Enterprise can get out here that's near the trailing point. Now zoom right, because now you're all familiar with this. Antijovian, we cover really well. And here comes the leading point, is this big guy in the back, which again, we're not getting close to, and we have to watch from afar. And why is that? Because now you're experts in this. Who, if our spacecraft flies by, right, if it's making flybys, it's going to fly by the far side or the near side compared to Jupiter. But if it were to try to fly past the trailing or leading, it would be crashing into Europa. We don't want to do that. So we can fly by between Jupiter and Europa, or we can fly outside the other side compared to Jupiter, the antijovian part closely, but we won't get close to the other planets. So we have to see them more from afar. Let's see. We have time for cool animation. How are we doing? I know you're good.
Yeah.
Or there are freshmen in there. Let's look at a typical flyby. I haven't tried narrating this thing since my last public talk 5 years ago, so we'll see how I do. But what you're going to see, this is an older version of the spacecraft. It won't look just like ours, but it's pretty close. And what you'll see is in the flyby configuration, we talked about that, the solar arrays are facing the direction of motion, and the remote sensing instruments are looking down at Europa. The mass spectrometers are ahead, the bug's tail is facing the back, the magnetometer, and the radar needs to be parallel to the ground. But when we're farther from Europa, we sure want to be charging the batteries that are operating the spacecraft during the flyby. So the solar arrays will be facing toward the sun, and generally the high gain antenna will be pointing to Earth, transmitting data. So we have the charging position, if you like, when we're far away, and then the flyby position when we're closer in. So the solar arrays articulate compared to the body of the spacecraft. So, and then we'll see the fields of view of the various instruments. You'll see them flashing gray when those instruments are being used. Again, this is notional, but it gives you an idea. In the bottom right, there's too much going on in this book. In the bottom right, you'll see the spacecraft come in on its orbit and meet up with Europa in its orbit. And on the top, it'll show which the orientation of the spacecraft, which mode it's in, and which kinds of observations have been done. Again, more than we need to know, but you'll see that all the instruments go on the fly box. So let's try this out. First, there we are, charging the solar arrays and turning so that the remote sensing instruments are now facing to Europa, but still kind of orienting so we're getting some charging of the solar arrays at the same time. That's the ultraviolet instrument making some scans. It can't scan, so the whole spacecraft has to nod to make ultraviolet observations. That was the thermal observation. So now the spacecraft rotates and is facing so that the particle instruments can also start getting measurements. There, the whole spacecraft nodded again, so the ultraviolet and the infrared instruments can take data. The cameras can move, the infrared spectrometer can move, the other ones cannot. So now we're zooming on, lots of instruments on, making observations. The big flashes are the wide angle camera as we're zooming in. And then it's going to rotate one more time now to put those solar arrays in the configuration so the radar will work during the flyby. Now we're in the flyby configuration, all instruments on at once as we do and collect all this data at once. This whole sequence takes about 2 hours on each side, so about 4 hours is represented here. And we do the same thing in heels and backwards as we pull away from Europa. And then with this bounty of data, doing this about 49 times. The spacecraft will again reorient, put the high gain antenna in the direction toward Earth, and put those solar, we'll do that joint scan one more time on the way out to get that global view of all the instruments, and it'll orient the solar rays again toward the charging position. So one of these days, I'm going to work it so I can make my little model do that to the globe. I'm not quite there yet. There it is.
How long will it take you to get signals back?
Well, let's see. So the light time isn't the problem, right? 40 minutes or something like that. But the issue is, when do we get the passes so that we can send the data back to the DSN, to the Deep Space Network? And we also have to do some massaging, some operations to transfer the data from one place in the data storage unit to another place in the data storage unit. And that takes a little bit of time. So I forget, but it's probably something like 12 hours after the flyby that we can start transmitting data back. And we're not going to get all that flyby's data on that pedal during that orbit. Some will stay there and it'll build up over time. And then we'll get some times where, oh, there isn't a Europa flyby for a while, and we can slowly blast that data down over time. We're flying by Ganymede and broadcast the data down during that time. A couple more questions in the back, if you can pass the mic around.
I have a couple of questions. The first one is the Juno mission providing any useful information on your mission? And the second question is this mission impacted in the same way the Psyche mission is the same software?
Okay, good questions both. Juno mission. So you are a knowledgeable person when it comes to missions, I can tell. The Juno mission, we had a nice talk by Scott Bolton, the PI of the Juno mission, just a couple weeks ago. And the data is very preliminary. So the one thing that's obvious that is helpful is that nice global image from Juno of Europa is of an area that's poorly covered from Galileo and Voyager. So it's kind of kilometer scale imaging, but it's of a region of Europa that we haven't seen very well over here in the leading hemisphere, where it's kind of blurry. So that'll help somewhat with adjusting our trajectory. We're making some final adjustments to what that trajectory will be like, and the Juno images will be handy. Wow. That's other question was Psyche, and you're aware that there were some issues where the software wasn't ready, and so Psyche got delayed. And believe me, we have a magnifying glass on Europa Clipper right now, and we're 2 years out, and the software is just about done. So I'm happy to say that. The other issue mentioned in a report that just came out about why the Psyche mission got delayed was related to staffing issues. You know, a lot of people come, and companies come and suck people out of JPL and offer them lots of money to go up here or up the coast further. And so we're very carefully working with management at JPL to ensure that the Europa Clipper mission is properly staffed. So we're looking ahead to, like I said, when those people doing the build in the clean room will go on double shifts in January, and making sure we've got enough people for their job. It's one back there.
So what's the total flyby time before it crashes?
It was, what did it say, 4.27 years, something like that, from the time we entered Jupiter orbit to the time of impact to Ganymede. But impact will probably, if the spacecraft is doing well, get extended, and I wouldn't doubt if it's past that time. So then I'll always be sipping martini somewhere and going, oh, let's do this.
In the vastness of space within our solar system, there are, I presume, other satellites that are up there, and also space satellite debris that's up there. So what is this satellite? And or I know you have the launch window. What are the features on the satellite to ensure that it does not get damaged from or hit another satellite?
Oh, okay. I mean, and that's a question for all satellites around Earth. And there's a whole network of folks. A good friend of mine works at a telescope in the middle of the darn Atlantic, searching for space debris. We know where every little piece is, and it's being tracked extremely carefully.
Okay.
So not to worry about that. And something I forgot to mention, that I should mention, these flybys are at an altitude of generally 25 to 100 kilometers off the deck at Europa, extremely close. Yeah.
Is it, would it be possible on a future mission to just orbit or satellite orbit around Europa? Or is there too much interference with Moon, Jupiter?
Back when I got into this biz in 1998, when the first science definition team was being stood up, the idea was a Europa orbiter. And right up to about 2012, the default was we're going to orbit Europa. But what's the problem? We've talked about the radiation environment. And so let's just Austin. So if Europa Clipper, or maybe that orbit, this spirograph showed up pretty well, right? If we're in orbit around Europa, then we're immersed in the radiation environment from Jupiter. But that radiation dies off as we get further away. So the spacecraft can live much longer by making flybys and getting out of the radiation environment. So if we were an orbiter, it would live a few months of the radiation before you get to that 3 megarads of total dose. Would make the mission more expensive to try to radiation harden all of the parts. Whereas this way we can take the flyby, transmit the data slowly, and end up getting a lot more data, it turns out, through this approach. But we don't have the uniform global coverage that you'd have if you were an orbiter, and so we get some bald spots.
I'm just wondering, I know trying to get the bird off the ground now in the next couple of years and then time and catch that data, but giving forethought to an eventual lander, is there technology available yet to be able to get through the ice? I know that's something that's been worked on for quite some time with some sort of thermonuclear melt thing, and you got to put some sort of relays in the ice as you go down to drop a smart bot into the pond.
So the reality of it is it's pretty darn hard just to get a lander onto the surface and survive for 30 days and scoop some stuff up and test that material and search for life, as I hope we'll do after Europa Clipper. The next step, though, the next logical step is, can we get through? If we were to find signs of life right then, it would be, hey, it's worth it to spend money and see if we can get down in there. It's a very hard problem, but yes, there are people actively working on the steps of how one could probably melt down through the ice and get into the ocean. But I'd be surprised if we saw it in take a few questions, but a few more questions, but let me make sure that I thank the Europa Clipper science team, many of whom are here in this picture, and this also includes many of the engineers working on the project. It's amazing.
Yeah. So the other moon I've heard, seems similar to Europa is Enceladus on Saturn. Is there any kind of competition between where the funds go between those two?
Well, read the book, The Mission, and you'll see that what headquarters did for a while there in 2007 and 8 was to have a competition of should we go to Europa, Ganymede, Enceladus, or Titan, and propose a flagship mission. And the Europa team Europa had a head start because we had been looking at concepts for a long time, so we kept coming out ahead. but it helped to develop concepts for those other worlds. So there's something called the decadal survey. Planetary scientists get together every decade and put together a plan and recommendations. And it was Europa for 2 decadal surveys in a row before we got a mission going. The recent decadal survey came out this past year, says, go to an ice giant called Uranus along with the probe, and then next on the list is an Enceladus mission that might both orbit and land. But it also says, hey, maybe we can do a cheaper mission, New Frontiers style, as it's called, mission for only $1 billion instead of a few $1 billion for the big flagship mission. Maybe that can do something smaller at Enceladus. So yeah, there's good cooperation now because we understand the progression of the sequence events. There is Dragonfly going to Titan. There was a very tense time in around 2007 when it got a little hot and heavy in terms of the competition. And yeah, we're the community is still healing from that. It was good in promoting the outer planets and understanding the definition of missions. It was difficult in terms of some of the personal relationships, unfortunately. Yeah.
On the page that has the spider graph
Yeah.
image, are the different colors, are different things detecting stuff?
The different colors here are the different phases of the trajectory that build up this kind of map. So what happens is there's a sequence of maybe, 5 or 6 flybys all in a row, and then another sequence that comes and cuts across those, and then another one in the other hemisphere. And the way that tour designers build up this coverage in a really brilliant way is mapped out in the different colors here. And they could, better than I can, show how these different phases build up to create the whole. First, we concentrate on the antijovian hemisphere and flying by. First, we concentrate on the antijovian hemisphere and flying by it when it's lit, which would mean Europa over here, and flying by outside of Europa's orbit. And then we concentrate on flying by when Europa is in this position relative to Jupiter and the subjovian hemisphere is lit to build up the coverage of Europa.
Thank you.
So yeah, what I didn't bring, I think I have to insert it into my talk, is a movie of this spirograph all building up. And these COT sequences, and they have all these codes for the different phases of the orbit. Any other questions before we wrap up?
There's a question on the chat. I don't see any of them there.
There's our website, europa.nasa.gov. Learning more about the Europa Clipper mission there, and this has been a real blast to come talk to you.
Well, I think that concludes our program. If there's no more questions. Okay, all right. Well, good night, all. See you next year.
Stickers.